In your first session in evidence-based medicine this week in MCC, you'll be talking with Dr. Gren about statistical concepts like sensitivity and specificity of testing modes. In order to get you warmed up for that, for the second session where she'll be talking about how these concepts apply to a specific kind of testing for the virus, SARS-CoV-2, I want to go through these methods with you so that you'll have time to think about how they work and then how the statistical analyses apply to the way that the mechanisms of these testing modalities work. We won't be talking much about viral pathogens in MCC, but the concepts are quite similar, and you'll see these same kinds of tests being used over and over again. So what I want to do in this video is just walk through 3 ways you can detect a viral pathogen in a patient sample, or the exposure of a patient to a viral pathogen. So the 3 ways are going to be, we can look for the genome of this virus by using PCR. SARS-CoV-2 has an RNA genome, so we're going to have to use reverse transcriptase to use PCR, turn the viral genome into DNA. And we've talked about PCR in other videos for this class, so we'll go through that one pretty quickly. This is going to be the gold standard for detecting a virus because it's so sensitive. Second way, we can look for the proteins. So here's the virus. It's got its genome in the center. It's got these proteins sitting on the surface. The spike protein is the one you've probably heard about because it's the one that we're making vaccines against. And that makes sense because it's sitting on the outside of the viral particle, and making antibodies against that would help to neutralize it. So we can use that same trick to get antibodies and detect viral proteins in a sample that we've taken from a patient. The third way is going to be more indirect, but a similar antibody-based method. We'll be looking for a patient making antibodies against these spike proteins. So the sort of goal of vaccination is that you should make antibodies against this virus, and we can ask whether or not that's working, or if you've been infected with the actual virus, by seeing if you make antibodies against it. So those are the 3 methods, and we'll walk through them in this video. So the first one, PCR, we've talked about in other videos, so I just recapitulate that here by saying, well, we want an RNA genome, so we're going to have to extract that RNA from the patient samples, turn the RNA into DNA by putting in random primers. Here's random primers that'll anneal to anything. They're just short primers that we don't have to worry about their sequence too much. And we use reverse transcriptase, this enzyme, to turn the RNA in blue into DNA in brown here. And now we can do normal PCR. We can take specific primers, these 2 guys, and amplify a region of the target genome, something that we've chosen as an acceptable target. And we'll go through multiple cycles, maybe 30, maybe 35 cycles, and we can turn a single molecule of the genome into something like 1 billion particles of the genome, copies of the genomic sequence, which is detectable by various physical methods. So this is an extremely sensitive method because I only have to have 1 molecule of the viral genome in my sample, and I can amplify it in an hour or 2 into enough DNA that I can see it by physical detection. So extremely sensitive, single molecule detection. I'm not going to miss many things, so I don't have to worry about false negatives with this technology. So the PCR test you've probably seen mentioned, or maybe even had the PCR test. This is the one that we started with and started looking for people's infections this way. Extremely sensitive, very specific. The second test, the one that's been used more recently, is a rapid test. Whenever you hear that term, a rapid test, you're probably talking about an antibody that detects an antigen in the sample, because this can be done in a few minutes. Even though the PCR test only takes an hour or 2, the workflow requires that this takes a day or 2 to analyze, to get enough samples together to make it economically feasible. But these tests, these rapid tests, you can do in a few minutes on site with individual samples, so you don't have to pool them together. So this is what they're doing, say, at airports before you get on an airplane. They'll do a rapid test to see if you've been exposed. And we'll talk about advantages and disadvantages of this at the end. Okay, so in this test, what we have to have is an antibody that recognizes, say, the spike protein. So we've made an antibody in some other animal, and we have labeled it. So say I go to a goat, and I inject the spike protein into a goat. It then mounts an immune response. I take the antibodies from the goat, and I label them with something. This gold dot here is something, a fluorescent tag or a radioactive tracer, or most of the rapid tests that you would do on site would involve putting an enzyme on there, like horseradish peroxidase, that you can then put in some sort of a substrate and have it turn color. So this is the basic features of the rapid test are: I have made an antibody in some other animal, I've labeled it some way that I can detect, and now I take my sample from the patient and I put it on a slide. So we've got the viral particles sticking to a slide of some sort, and now we come along with the antibodies and we say, antibody, can you find your antigen on this slide? If it sticks, I detect the detectable label, and I say, okay, you have the virus in your sample, so you must be infected with the virus. This is not as sensitive because I have to, the sensitivity now is determined, the physical sensitivity, how well the test works. This is distinct from the concept of statistical sensitivity that you'll be talking about with Dr. Gren. But whereas I could detect one molecule of the genome of the virus with PCR, I'm going to have thousands or tens of thousands of them in order to detect the antibodies stuck to the sample. And the detection limits are going to be determined by the detection method. The on-site ones with horseradish peroxidase, I might need 10,000 molecules. I can do this with a fluorescent tag in the lab, but now I have to have the sample processed in a lab. So sensitivity, physical sensitivity, is going to depend on how well I can detect the antibody and the thing that I labeled it with. The third method is also an antibody-based method, but now I'm asking, I have purified the spike protein and I put it on the slide. So I have this slide covered with purified spike protein, and I take the sample from the serum of a patient. I say, I want to see if you have been infected with this virus by seeing if you mounted an immune response. So now the blue guys are human antibodies taken from a patient, but I can't detect those. I have no way to detect a person's antibodies, so I have to make another antibody, much like the goat antibody against the spike protein that I had before. I go and I make an antibody in goats or donkeys or rabbits against human antibodies. So now the antibody will recognize a conserved part of human antibodies, and I do a second stain. So first I put in the human's serum to see if those antibodies will stick to the spike protein that's sitting on the slide. And then I do a second step where I come along with anti-human antibodies, and I see if I can detect the human antibodies. So this is going to decrease the sensitivity a little bit more. Again, it's an antibody-based method, so my detection is going to be determined by how well I can detect this label that I put on the antibodies. So I'm going to need thousands or tens of thousands of molecules, of the antibody molecules, in order to detect this. Again, I put purified protein down, and I ask, did this person make antibodies against this purified viral protein? So in addition to the sensitivity, the physical sensitivity of these tests, there's also a timing issue. So here I've shown sort of the time course of a viral infection. In purple here, I've shown how much virus there is in a person's sample, the sputum or the nasal swab that we took from them. You'll see that since the PCR is so sensitive, I'm going to detect it quite early because I only need a few copies of the viral genome to be in the sample. So here time is in weeks, and I'm going to be able to detect a viral infection in days, maybe 1 or 2 or 3 days. I'll be able to detect this by PCR. It's going to take longer for the viral titer to go higher before I'm going to be able to detect it with an antibody test. So that may take 3 or 4 days. And this is sort of the problem with these tests right now, is you may go to the airport and get an antibody, a rapid antibody test, and it'll come up negative, but you might be down here in your infection course. So it doesn't necessarily tell you that you aren't infected. It says you haven't been infected. The infection hasn't gone very far. So you're going to have the problem of false negatives with any antibody test because it's not as sensitive physically as a PCR test. Eventually, if you have been infected, it's going to take some time because it takes about 6 weeks for you to respond, your immune system to respond to this attack, and it's going to take about 6 weeks before we can detect antibodies in your serum. So there are timing and sensitivity issues that go on with all of these tests, and you'll be talking about how you analyze that statistically with Dr. Gren in your second evidence-based medicine session. So think about the concepts of statistics that you'll be learning in the first one and how you're going to apply them to a real-world test for a real-world viral pathogen in the second session.